Hi, I'm Byron Patel. I'm with Burns McDonnell. I work out of the Atlanta office. I'm in the Substation Design Group, and I'm here today to talk to you guys about lightning protection for substations using Lee's rolling sphere method. You'll find this outlined in IEEE 998, specifically in section 5.3. All right, so what we're going to talk about today, we're going to discuss the fixed angle method, some of its shortcomings, and why there's a need for another method. And then we're going to go right into Ralph Lee's rolling sphere method. Then we're going to discuss some of the different geometries for the different protection zones it provides. And then we're going to analyze the reliability of this method using failure rates. And then we're going to go right into the online software where I'll show you a calculator that we've developed that will allow you to calculate these protection zones and allow you to test your substation's protection. So the fixed angle method basically states that you can erect a mast in your substation and everything inside its 30-degree window will fall inside its protection. So right here you can see we've erected this mast, and the equipment that falls inside this dotted line, inside its 30-degree window, is considered protected. Now there's a few shortcomings to this. One is that it doesn't really hold true to very tall situations, to situations where the mast is much taller than the equipment height. For example, the Empire State Building is a very tall structure. However, buildings inside its protection zone, its 30-degree window, have been subject to direct lightning strokes. Another theory says that, well, if this is accurate, then the simplest solution to protecting your substation would be to just erect a really tall mast in the center of your substation. Even though that may not be economical, it would be the simplest way to protect your substation. And we found out that this isn't true, and items are still subject to direct lightning strokes. Other shortcomings of this method are that it provides only a binary protection analysis. That means either everything is protected or not protected. It doesn't account for varying stroke current magnitudes. So if a stroke current is greater than another stroke current, we can't say, well, it protects against this current, but not against other currents. The electrogeometrical model was then developed. It was developed in 1971 by the Edison Electric Institute for Transmission Systems. Very shortly thereafter, a gentleman by the name of Ralph Lee simplified it and modified some of the formulas so that it was ideal for substations and buildings. It was then shortly thereafter criticized by Ericsson and Anderson, but then later in the late 70s and even 1980, Mousa and Srivastava, they worked together and they eliminated a lot of these discrepancies, and that's what we use today, and that's what you'll find in the IEEE 998 Section 5 today. All right, so to understand how the rolling sphere method works, we first need to understand a little bit about lightning strikes. And the way lightning strikes work, first you start off with a thundercloud. Now a thundercloud is a cloud where a charge separation has occurred. This charged thundercloud will then ionize the air around the cloud, forming these little step leaders. And they're formed in random fashion. Well, eventually they'll make their way closer to the ground. When they're within striking distance of something with the ground, a return stroke is formed. The return stroke is that bright bolt that you see. It really carries the muscle of your lightning stroke. It has the high current, and it's the one that can be dangerous to your substation. It goes from the ground, either through an object or through an air, going back the path of the step leaders, back into the cloud, and then neutralizes that cloud. The stroke current is a factor of your strike distance. Here's that formula, and we're not going to go too deep into the formulas here today, but it's the distance of your last step leader. All right, so what level of stroke current do we need to protect against? Well, that's given to us from our basic impulse level, or BIL, also known as your basic insulation level. Your BIL is the maximum amount of voltage that your insulator can withstand before flashover. IS, the allowable stroke current, that's associated with that BIL, is the allowable stroke current, and that's calculated by the following formulas from IEEE 998. Now, this is the stroke current, the minimum stroke current required to cause flashover. Well, what about stroke currents that are greater than IS? Don't we care about those as well? Well, if you can protect against IS, you protect against higher stroke currents. And let me explain why. That's because the greater your stroke current, again, from this previous formula, the greater your stroke current is, the greater your strike distance is. Well, the greater your strike distance is, that means that step leader, that return stroke, has a greater reach. And it favors grounding electrodes and shielding mass simply because a shielding mass is very tall, there's less air insulation, there's no insulator to flash over, so there's less resistance back to the cloud. So when it has a choice, when it has an option, it's going to take the grounding electrode or the shielding mast or the shield wire instead of your equipment. So if you can protect against the stroke currents that have the shortest reach, which is the minimum allowed stroke current, if you can protect against that current, then you can protect against the ones that have a longer reach, because again, the ones with a longer reach will have a much easier time finding that mast or finding that shield wire to travel through. Now, this formula shows for BILs less than 350 kV, we just fix the stroke current at 2 Ka. Well, why do we do that? Well, the reason we do that is because at BILs less than 350 kV, this calculated stroke current is very small. And so the reach is very small, and it becomes very difficult to protect against those stroke currents. It just becomes more practical than designing for even smaller stroke currents that won't occur 99% of the time. All right, so what is the strategy behind the rolling sphere method? Well, a step leader can originate anywhere in a substation. But if they're within striking distance of the ground or a ground electrode, again, we have nothing to worry about. It's going to take that mast or that grounding electrode or that shield wire instead. It's the ones that are not within reach of a mast that could be a problem, especially if they're not within reach of a mast or not within reach of the ground, but they are within reach of your expensive equipment. So to test a design, we need to see if there's a place where a step leader could form that can't reach a mast but can reach equipment. So to do that, we create a sphere with a radius equal to the strike distance that's associated with IS. Again, there's some formulas. We're not going to go too deep into those formulas right here. Then you want to roll your sphere through the substation going up and over your shielding electrode. So every time you run into a mast, you go up and over it. And I'll demonstrate that here. So we have created our sphere that is equal, that has a radius equal to our calculated strike distance, and it is rolling in from the left side of the screen, and you can see there's a mast right here in the center of this picture. So we stop at the mast and we go up and over the mast. Any equipment that is underneath this curved surface of this circle is considered protected from direct strokes. So that's shown here by the shaded green area. So in this example, everything in the green area is protected, and then you can see right here, this little piece of bus is outside of the protection zone and is potentially subject to direct lightning strikes. Well, let's look at that a little further. So in order for that to happen, a step leader has to form very close to this X that I've demonstrated here. This is the center of this sphere. This is where that step leader occurs, where it cannot quite reach the mast, it cannot quite reach the ground, but it can reach this bus. Now that is, again, for that specific stroke current. If our stroke current was any larger, our strike distance and our reach, therefore, becomes larger. Well, why exactly is that? Here's an example showing two different spheres from two different stroke currents. Again, the larger your stroke current, the greater your strike distance, and so the larger your sphere and the greater your reach. As you can see here, with the red circle represents the larger strike distance and the larger sphere, there's a much larger area underneath the sphere as compared to the blue. Again, with the previous example, if a step leader forms at this X, it could, that has this given stroke current to create this size circle, it could strike this bus. But if the stroke current is, again, just a little bit larger and it forms in the exact same place, you can see now the mast is within reach and the ground is within reach, and so it won't strike the bus. So the only thing that's really dangerous to that bus is stroke currents of a particular magnitude that form at that X. Again, a small window of stroke current. So you can see this mast actually does provide protection to this bus, even though from our analysis it's unprotected for that particular stroke current. For greater stroke currents, it does provide protection. You may have noticed that the optimum mast and wire height is equal to S, your strike distance. Well, why is that? Here's an illustration that shows that. When you're rolling your sphere across your substation, result that gives you the greatest area under your curve would be a mast or a wire that stops the sphere right at this 3 o'clock point. That gives you the greatest area under here. Here in this example is a wire, the wire going through the screen and providing the same protection. Now a mast that's taller than S has no effect. It's not going to increase your protection. It's not going to stop the sphere any shorter or any later. But a wire that is taller than S can actually reduce your protection. Well, why is that? Well, here's the mast that's taller than S, and you can see again the same level of protection provided. But a wire that is taller than S could be a problem. If the wire is taller, the sphere can actually begin to roll underneath the wire. As you can see, the protection provided here underneath the red curve is much less than the protection provided underneath the blue curve when your wire is at the height of your strike distance. The height of your equipment affects the radius of your protection given by your mast or wire. And why is that? This illustration shows that we have two different equipment heights. The shorter equipment you can leave further out from your mast. Now this is a good illustration of radius of protection, is how far out from your mast can you place your equipment. And as you can see, the shorter your equipment is, the further out you can place it before it's subject to direct strokes. Your BILs and your conductor impedance also affect your strike distance. Again, here are the formulas that illustrate that. You can see that your BIL affects it, your conductor affects it. What does this mean for you? That means when you're calculating your protection radiuses and your geometries, every time you have a change in your BIL, for example, if you have a transformer and you have a high side and a low side, you're going to have two different BILs. Every time you change your BIL, you're going to have to take that into account when you do your calculations. Every time you change your equipment height, you're going to have to take that into account when you do your calculations. And again, every time you change your conductor, it's going to affect your conductor impedance and then affect your strike distance and stroke current.